So today we are going to talk about, it's another concurrency talk. The first concurrency talk I gave in C++ India conference 2022. So this is the second concurrency talk. This is based on active objects architecture pattern. So this is a slide which is kind of a copy paste from my previous talk because I want to make sure that everybody is on the same page on what we are discussing here. So you must have heard about these design patterns like observer, command, factory, singleton. But this talk is not about design patterns, it's architectural patterns. So what is an architectural pattern? So architectural pattern is basically, the definition is it expresses a fundamental structure organization schema for a software system. So it's basically a pattern using which you design a software system. So there are many well-known architectural patterns like MVC, microkernel, layers. So this talk, we are going to talk about active objects, which is an architectural pattern. Okay, let's dive in. So let's do a system design. So all my talks here and in my company, I like to do a system design, and I think that's the best way to learn a pattern or a technique in software. So let's start with the system design. So let's see what we are attempting to design today. Okay, so here is a top level overview of the system, which we will try to design today. So this system, sorry. So we have a user. So this, what the system does is basically it has some kind of a graphical, some kind of a user interface. It could be graphical user interface. It could be a CLI. It could be API, some kind of user interface using which the user interacts with the system. And this system does many things. And one of the things this system does is this system talks to a backend cloud service. It could be like OpenAI or AWS or Azure, Google Cloud, whatever. So it's a backend. It talks to a backend cloud service, which so there is some machine learning model there in the cloud service, and this system talks to that machine learning cloud service and does an inference. To give an example, this could be a OTT platform which you're trying to design, where there is a user interface which shows different movies and reviews, and there's a backend which is basically talking to a cloud service to get you some recommendations based on your user, based on your viewing pattern and stuff. Or this could be something like a chat GPT, which is like there is a chat GPT in the backend or GPT-3 in the backend, and you have developed your own system using that, and your system is doing something like translating some information or extracting emotions from a text or something like that, or helping our development tool, which kind of helps you write a better code. And your system is basically taking the input from the user in some form and then talking back to the cloud and getting the inference done in the cloud. So this is what we are going to try and design. So the problems here are, the first thing is the user facing component. It could be a thread, it could be multiple threads. So user facing component cannot block because it's basically continuously processing the user inputs in some form. The next thing is, if you ever worked with an AML web service or AML REST APIs, you know that it's not very predictable, the response times. I mean, you cannot make any kind of assumptions in your system that you will get some response in certain time duration. So it could vary from a few hundred milliseconds to seconds. So even the best of the ML services I've seen, it takes, because the nature of the inference, because the input is unknown. So the response times are unpredictable. And the backend processing, it's not only getting the data from the ML service, it's also doing some other things, right? So there could be multiple execution units in the backend also. So doing some other stuff, interacting with the database or whatever. So it could be multi-threaded or in some way multi-processing. And the overall design is our goal is to have a clean and neat design, and follow all good design practices and principles. So let's, in today's talk, we will try and design the system. There are multiple ways we can design such a system. But today we are going to see one of the ways which we use to design a similar system. And I believe it's one of the simplest and cleanest way to do this. And we are going to use active objects, which is the topic of this talk. So before diving into the design, let's first try to understand what is this active object architectural pattern. So this is the book, Pattern Oriented Software Architecture, Volume 2. If you are interested in designing software architecture, I would recommend all the 4 volumes of this series, and it's kind of a Bible reference for me for software architecture. So highly recommended. So the definition of active object is from this book. So what is an active object? The active object design pattern decouples method execution from method invocation to enhance concurrency and simplify synchronized access to objects that reside in their own threads of control. So I know it's a mouthful, but let's focus on the highlighted item. So it's the core of active object. It decouples method execution from method invocation. So let's keep this in mind throughout this talk. I mean, I will be emphasizing this point at multiple points in this talk. So it's basically what we are trying to do is we are separating the method execution and method invocation. I hope by end of this talk, this sentence makes sense. So let's move. So what we are saying here is, so there is the method invocation happens in a different thread, and the actual method execution happens in a different thread. And the decoupling is such that it's clean decoupling in the sense that the client which is causing the method invocation does not know that method execution is happening somewhere else. For the client, it's like invoking any ordinary method. So this is again the key of this architectural pattern. Okay, so yes, let's move forward. So before this, any questions? Please, I think you can ask any questions. If I will try to answer, and if not, I have allocated 10-15 minutes of Q&A at the end. So yes, let's continue. So let's go through some of the components involved in active object design. So there are total 7 components, but it's kind of 6 components. I will tell you what I mean. But don't be overwhelmed by this. We will try to break this down, and it's not as difficult as it looks. So the first component is a proxy. So this is the component which a client, when I say client, it could be a software, it could be another system component. Okay, so I'm using client in that meaning here. So whenever a client interacts with the system, it interacts with this proxy object. So the invocation of the method happens in this proxy object. So this proxy object provides the interface to the users. The main component here, one of the main components here is this command. So there is an abstract interface which defines the commands which corresponds to the user request, and there is a concrete implementation of those commands. So we will see example of this. And then there is this activation list and scheduler. So the commands are then added into the activation list. So, and there's a scheduler which goes through this activation list, and based on certain criteria and defined by the programmer, schedules which commands needs to be executed. And the executor then takes this commands ready for execution and then runs the command. Okay. Now the question here is, how does the user know when whatever the user requested the operation is completed? So what the proxy does is, when a user creates, whenever a user makes a request for any operation to be done, the proxy returns a future to the user. So there is the future object which holds the result of execution. So we'll talk about future a bit more in this talk. For now, just remember that the user gets a future, and when the executor completes the execution of that request, the future will hold the result of the execution. Okay, so let's see the dynamics of this. I hope this will make things a bit more clear. So what's happening here is a user. The first the user makes a request. User or client, makes a request. The proxy provides with the interface. What the proxy does is it first creates a command for this request and adds into the activation list, and the proxy returns the future to the user. So at this point, the future does not hold a result. Okay. And what happens then is, there's a scheduler which goes through the commands in the activation list and schedules a command to be executed. And the executor then actually runs the command. So once the command is run, the result of that execution is set in this future. So there is this dotted line through which the result is set. So for the user of the system, for this when he invokes any request, the invocation returns a future immediately. So there is no blocking here. Now, the user of the system, it behaves as like any normal request. So you make a call, you get a return value, which is a future, and you proceed. But the thing is, this future then will hold the result of the command which is executed. Now this proxy is running in a different thread, and then this executor. So there are two different threads, a minimum two different threads of execution here. So, and the only thing which is shared between these two threads is this activation list. Okay, so let's see some of the salient points of this design. So if you see, the only shared object here, or the only thing which is shared, is this concurrent, is this activation list. What it means is you need not do a lot of mutexes and logs anywhere in the program. The only thing you have to synchronize is this activation list. The only concurrent object here is this activation list. So so you do not worry about locking any of the other components or anything. So it's just you have to just make sure this activation list is accessed by 2 threads concurrently. So you have to make sure that this activation list is thread safe. And also the other thing is the command, the different components here have well-defined responsibilities. For example, the proxy does not know about how the commands are executed, and the executor does not care what the how the execution object is, because that is implemented by the command. And the command basically does not care whether it's proxy or executor. It just knows how to run a particular request. And the scheduler, of course, just know how to schedule based on some hooks provided by the command. So each component here is fairly isolated, and they follow a good single responsibility principle. So it's easier for us to maintain such a system, and easier to extend as well. So we will see the code, of course. You can the C++ implementation of this, it's pretty straightforward and simple. So we'll see this. Okay, so now we know the dynamics of active object, right? So before we see how this is applied to our system design, which we want to do, I want to talk a little about promise and future. So promise and future, these are not new concepts. This has been these are very old concepts, as old as computer science itself. So so in a typical async programming, or if you want to do some kind of async operation, there is one of the ways to use promise and future. So what is a promise and what is a future? So you can think of promise and future as two different objects, but they are entangled in the sense that they have a shared state. So, and promise is something which actually set the value to the shared state, and future is some object which actually gets the value from the shared state. And these two are, so typically a promise is something which resides inside the library, and the library gives you a future to the users of the library, so that the users can get the results out of some operation, right? Many different languages, in fact, all major languages have some support for promise and future. In C++, since C++11, we have support for promise and future, and every edition of C++, there is some improvements in this, and in C++23, we have more powerful future object. So so basically you can think of this as a shared state, which is then set by one object and get by other object. So this is kind of one of the crucial components in our system design. And we'll be using this C++ feature in our implementation. Okay, now let's take another look at our system design we want to do. So we have this CLI thread which takes input from user, and it does bunch of things, and one of the things it does is to do a machine language inference from a cloud service, right? So let's see how we can apply active object here. So what we have is our user here is the UI thread. So user interface thread. So this component is the user of the system. So we have a proxy. We all know what is a proxy now. And what the proxy does is when a user gives a request, suppose to do a recommendation, to get a recommendation for certain movies or music. So the user, the UI thread invokes request for the recommendation. So proxy gives it, what the proxy does, it creates a command for this request and gives back a future. Okay, now this command has the promise part of the future. So promise is not exposed to the user. Sorry, anyone? I think somebody. Any questions? Okay, so the proxy returns the future, and the corresponding promise of the future is inside this command. Okay, now if you remember the dynamics of the active object, so we had a scheduler and a list. But in our system design here, we want to make things a bit simpler. So what we have done is we have created a thread safe queue instead of a list. So what it means is a queue, this is a FIFO. And because we don't really care, we don't want to do some kind of scheduling, because in this system, it just first in, first out. So whatever requests first, it gets processed first. So we have eliminated the activation list as well as the scheduler. So instead of an activation list and a scheduler, what we have is a thread safe queue. So the proxy here pushes the commands in the queue, and the executor here just reads the commands from the queue and executes those commands in an execution loop. Now, in the execution loop, the command objects itself have all the information to execute that particular command. So in a classical active object design, you need not have that. I mean, the executor can have some knowledge of how to execute a particular command request. But in our system design, just to make, because it's a bit simpler system design, so and just to make it's more cleaner, I believe. So all the execution knowledge of the command is in the command itself. So the execution loop just calls a particular method in the command, which executes the command and gives the result. And the command holds the promise for the future. So when the command is executed, the command sets the result to the future. So basically, the command will access the cloud service based on whatever needed by this UI thread, and then it gets the response, and it does just sets the future. Now, the good thing here is in C++, the future can also hold an error. So the error handling becomes pretty much cleaner, I would say, because now if the command is executing here and it encounters any error, it can set an error in the future. So future, you can set an error. Also, you can make the future through an exception. So if you are using exceptions to handle errors in your system, you can do that as well. So yeah, so in our system here, we have just we have eliminated two components. So we have proxy, we have a queue, we have an executor, and we have this command objects. So it becomes simpler and straightforward. So let's dive into the implementation of this. So all this code example, these are not slideware. This actually execute, and I will provide the link to my GitHub, so you can go and take a look, and you can use it as you want. So it's you can check the license there. It's open source license, so you can use it. So let's see the components. The first thing we will see is the command interface. So what the command interface has is basically a method to get future and execute. So this command, if you call execute, it will execute this command. Okay. And don't forget to have a public virtual destructor. We will talk about some improvements later in this talk, so where we can eliminate the virtual calls. But I'm going with a classical OOP here, so that we just focus on the active object pattern, not some other patterns like CRTP or type erasure. So this is the result. So this is just a sample result. So this is the result which will be set in the future. So we have some data and we have some error. So here I'm not using an exception. I'm setting an error string, and this is the result data. So any recommendations you get a string of recommendations. Okay, so this is what the future will hold. So now let's see implementation of a concrete command. So there is a recommendation command. So what we have here is we have to implement the get future and execute calls. And the important part is you can see that this has the promise. So the promise holds this promise, and this future which it will return is kind of they are tangled. They form the pair. And you can have and this implementation will have all these methods and data which is needed to make the call to the cloud service. So it will have all the logic here, everything. So the actual implementation of getting the data from the cloud service is inside this concrete implementation of this command. So the idea is you can add as many commands as you want. You can create different commands for different requests. So the next thing which you talked about is a concurrent queue. So this is a simple concurrent queue because this is the queue which will hold the commands. So I'm again going for simplicity here. This is a coarse granularity locking because I'm basically locking everything. And there it just two operations, NQ and DQ. So it just pushes the type data into the queue and it reads back. I just kept it generic because I'm just extending the standard library queue here. And notice the use of RAI logs. Always use RAI logs in your code. So this is a queue. Now let's see how the proxy looks. So corresponding to each command, you will have a method which the user will call. So get recommendation, get predictions. You can have. So every new method you add, typically you will have a new concrete implementation of a command, right? So this is the proxy, and this is the class which the user sees. I mean, this is the class which the user instantiates and calls the methods here. So what members this proxy has? This proxy has the command queue because this proxy will push the commands into the command queue. And this proxy will also have the executor object because this proxy will, as we'll see, the proxy will actually start the executor thread. So that's the executor task here. So let's see some implementation of this proxy. So what we are doing here is in the constructor of the proxy, we are just creating the thread. I have ignored the error checking exceptions here, but the idea is when you do a real implementation, you will have to take care of some. You have to check for some errors, but it's fine here. So what we are doing is we are running the executor object in the constructor. It just creates the executor object. Let's focus on the implementation of this get prediction. So what this get prediction does? So it just creates a prediction command and takes the future or gets the future from this prediction command and enqueues the prediction command in the command queue, and it returns the future. So that's all it does. I mean, it's 4 lines of code. So for any proxy, any kind of request, you just need to implement that method, which that interface which user can call. So it could be get prediction, get recommendation. If you have some image segmentation task, anything, you just need to add one method for that, and you enqueue the command, the correct command for that, and you are done. So that's the proxy. So the responsibility of the proxy is just to provide an user-side interface and queue the command. Right. So let's see the executor. So I have the intentionally kept executor as a generic class, because the idea I want to convey is the executor does not really care about what type it is using or how it is running. Here the executor is pretty simple. What it is doing is it is just reading from the queue and just calling the command execute method. So here is a bit of template magic, just to make sure, because the type could be here we are using a unique pointer to push into the queue. But it could be any object. So here, just to check whether it's a pointer. To more about this, I think the last week's talk from Ankur was pretty good on the template generic programming. So yeah, so here I'm just checking whether to call a pointer or a dot operators to call the execute. So the executor here does not care how the command is executed, and does not care how the promise is set. Nothing. It just runs a single loop to execute. So the good thing about this is, if you want, you can actually it is a very simple execution algorithm. But if you want to have something like you want a bit more sophisticated, you can do this without making any change in the rest of the system. So this is clean and beautiful C++. Now let's see how we use this proxy object. So the client. So here main is an example, but here in our design example, this will be in the UI thread. So what the UI thread does is just creates a proxy and calls get prediction and gives some input which it gets from the user, and it goes on and does other tasks, and it can check whether the feature is ready. So a std standard std feature has certain member functions where you can check whether the feature has a value. So you can do poll, or you can do several other things to see whether your feature is ready. So I'm just doing this get call. So the get call blocks, so it will wait till the results get ready in the future, and you get the result. So from the client perspective, you can see how simple the system has begun. You just make a call. It's like making a normal function call. You get a future, and then you just do your thing, and whenever the future is ready, you get the results. So it's very clean. There is no locking, of course, there is an internal locking mechanism between a promise and a future, but from a user perspective, there is no locks. There is no user did not have to care about the concurrency or anything, synchronization, anything. You just write code like a normal code, and you get the concurrency. So as I said before, there are many different ways to implement this system, but in our context, we chose active object because of this simplicity. Let's see some of the improvements we can do to this. We can make to this active object. The first is concurrent queue. As I mentioned, the concurrent queue, which I showed, I'm doing a course locking, which means I'm just locking the entire operation. But if you really care about performance, and it's a very high performance system, I would recommend to use a third-party concurrency. There are lots and lots of good concurrency implementations, concurrent queue implementations, which are very fast, optimized for their speed and stuff. One of the implementations which we typically use is from Absol. So you can use that. The other improvement is thread pool, the execution. So if you remember the execution code, it's just running in a single thread. It's just looping through the queue, reading the queue, and execution. So if any particular command takes more, it kind of blocks the execution. The execution loop will get blocked. So it may not give good performance. So the execution, you can move to a thread pool. And the good thing about this is all other objects and the user of the library need not care how the execution is done, right? So proxy, command queue, the commands need not know how the execution is done, or the user of this, the UI thread which uses this does not need to know how the execution is done. So you can change this execution mechanism whatever way fits your application. It does not affect any other system components. But in our real life application, we just use this single loop because it's not very critical for us to use thread pool or anything like that. And surprisingly, you will see that most of the applications will work with the single execution loop. So don't complicate your system if it's not needed. The third is, of course, I have eliminated the activation list and scheduler by using an concurrent queue because I just in this system we just need FIFO, and FIFO works well for us. But if your system is a bit more complex, where certain commands have higher priority, for example, and if they get added, so then you need to have an activation list and a queue. And in that case, typically your command will, let me go to the command interface. The command interface here will have one more virtual method, which will give some kind of priority or some kind of a guard, which tells whether it can run or not. So if with that you can with that hook you can have a scheduler which reads that whether it can run, or checks its priority and then schedules the execution. So that also you can do if it's needed. So here it's again, that's not going to affect the users. Of course, the two new components gets added, but the user of this library will not get affected in any way. So this is something you can implement if your system demands that. And the last improvement, we don't use unique pointer and virtual functions here because dynamic polymorphism is not necessarily needed here, because you already know beforehand the commands you want to execute, the commands which you have. So you can go to a different technique like CRTP or type erasure, and you can eliminate the uh, virtual calls and the base pointers in the command queue. I purposefully did not put it there because it will take the discussion in a different direction. I just want to keep focus on the active objects. So I used a classical inheritance, but and this will also work. I mean, virtual function has some overhead, but always measure that overhead may not matter to your application. So it's not that this is something bad, but you can, if you're really paranoid about using virtual functions, you can easily replace the command method with CRTP. And that's one of the reasons for having the execution executor as a generic class, because it does not care what it will, as long as it provides an execute method, you should be fine. The implementation of command does not matter. So it's all around, it's a very clean system design. Some more improvements can be done. I have not added in the slide, but before submitting the slide, I will add something. So when this entire thing is in C++ 17 implementation, because that's what they use. Unfortunately, C++ 20 we are not yet moved to, but if you are using C++ 20, okay, so things becomes a bit more simpler. Instead of this, again, instead of using CRTP or type erasure for command inheritance, you can use concepts, which makes things even more simpler. Again, go back to the Ankur talk. So the generic programming here looks generic programming, but as Ankur mentioned last talk, it can become a normal programming if you had if I had used concepts. And again, C++ 20 gives you coroutines. So maybe some other talk where we do the same system design using the coroutine instead of active objects. So that would be an interesting exercise to do. And I kind of have an intuition that coroutines will be even more simpler. But yes, I have not done that, but definitely I will try and see how it works. Okay, so if you want to extend this design, as I talked to you before, you can easily add new commands. You just add a API, the proxy for new commands, and you get new functionality in the system. So that's it. So you can look at this code in my GitHub, and the link of this book, it's here. I will add some more references here. So thank you for being here.